All right, and now, finally, to end our conference, I want to introduce David Cuartielles. He has shaped how the world learns, invents, and imagines technology. As the co-founder of Arduino, he's helped spark a global open source, open hardware movement that turned millions of ideas into prototypes. He is a professor here at Malmo University, an award-winning innovator, and he continues to explore how technology can serve both creativity and sustainability. Please welcome David Cuartielles to the stage.
So I really didn't know about the whole voting thing. I'm really scared now. I'm not prepared for this. I hope my jokes will not earn me bad points. So hey, how are you? I'm David, 51 years old, from Malmo. Anyway, I'm a teacher and head of a couple of labs at Malmo University since 26 years ago. So if after this talk you really want to work with me, please come to Malmo University and bring money with you because you have some budget cuts. We accept equipment, fika, anything. Also, I'm co-founder of Arduino. I will tell you now exactly what I did at Arduino. And since a month ago, I'm an employee of Qualcomm, as Qualcomm just purchased Arduino. If you didn't know, welcome to the new world. If you knew, we're very happy. I have to say this, we're actually super happy that this happened. Because now we don't have to go around begging for chips. Now we just have to do like this, give me the latest. And we will get it. This is our office in Malmo, by the way. So again, if you're here in Malmo, please come by for coffee anytime. At this place, you don't have to bring your own fika. We do have cookies. We don't have budget cuts. I'm also one of the founding members of the European Open Source Academy, which is a new entity we're building in Europe to promote collaboration in the production of software, hardware, and other things that are open. I'm the head of the Skills and Education Group as one of the founding members, and my seat will be running for the following 3 years. And again, we are now in the process of nominating the future awards for the 2026 edition. So if you would like to nominate anybody as a European champion, this could be someone working in Europe or somebody who was born in Europe working abroad, doing a great contribution to open source, then please let me know, and I will bring up this name to the nomination and voting, okay? I will run at the end of my talk because I don't want to see people voting bad things for me, so send me an email. Okay, so I will talk about bio-based electronics, but before going there, I have to ask you how many of you know about Arduino? This is great to be in this crowd. I was making a keynote on Tuesday at my hometown, and I asked the same question, and it was 10 people, and it was 400 people in the audience. But it was Mom, you know. Mom didn't say she knew anyway. So why am I here? Well, I'm here because I am responsible for this shape. I gave the shape to the first board, and I put the components where they were. As I was mentioning in the podcast before the talk, the first components for the Arduino boards were chosen because they were very, very cheap at a warehouse where an old lady had all components from the Olivetti factories that used to be around Italy. I'm also responsible for the bootloader in collaboration with Dave Mellis. Dave Mellis and myself were competing with each other to see who was making the best contribution to the source. And Dave, I think Dave won me. He made the last contribution in 2009, and that settled the discussion after many years of seeing. People don't really see it, but this bootloader is actually the most important contribution to Arduino. It's what allows people to program boards without having to press 2 buttons at the same time on the board, directly from the human-computer interface on your software. This might seem trivial, but it's not trivial in any way. Okay, this is really probably the most important contribution, making sure that people could continue to program things from their computer and just see that things were working here without having to like press a button to send and force the reboot. Until that moment, nobody has really done this properly. I'm also one of the creators of the Arduino forum. Currently, it's a forum with over 3 million contributors. In the beginning, it was me and 4 versions of me that had conversations talking about, hey, how do you plug the USB board to the board, the USB cable to the board, sorry. Because nobody really was like daring to ask the questions. So I asked the most stupid questions, invited people to like not to be afraid to ask, you know. But people started to make things out of these boards that we created. One of the funniest contributions that I find very interesting is Arduino. This is a one-man company from California, and he makes set of these boards every year for Christmas. So now that Christmas is coming, maybe you want to buy some presents for your friends. And it's used to learn how to program microcontrollers. But the thing is that you can also, the community contributed with that emulator you see on the right. So you can use the emulator to try out your games, and then you deploy on an actual physical game console. There is, I don't know, I think it's like 8 different themed versions of the console. And it's really like a business card size. And what is interesting is the chip you see here, this is the ATmega32U4, which is the same chip we have on the Arduino Leonardo, one of our boards. And during the pandemic, there was a huge lack of chips, as you know. So Kevin posted on Twitter, or X, formerly known as Twitter, hey, I'm running out of chips. Microchip's not willing to provide me with the chips right now because chips were using other things. And because he used this open source design where he was using the chips, we knew exactly what he needed, and we had that in our stock. We could just come back and say, you know what, call us because we might be able to help you. And he could sell his post-pandemic set of boards thanks to a collaboration with us. So yeah, this is one of the powers of open source, collaborating beyond software in this case. This is a piece made by Mar and Barbara, who's an artist couple that's currently in Riyadh, running the Interactive Arts Masters. But they made this stitching machine. It's a completely open source sock making machine that we exhibited in 2014 in Spain. And this is the speed we had to put it. Typically, this machine can produce socks at 100 meters per hour. But this was put in an exhibition for about 4 months. So we made it make like 5 meters of sock per day maximum, because otherwise the room will be filled up. It's an endless sock. You see, you just keep on adding thread to it, and it keeps on making sock and sock again. So it's for people with very long legs. And at the end of the show, we were like, oh, we would like to sell the sock. Who wants to buy the sock? Nobody wanted to buy the sock. So we went to donate the sock. Nobody wanted to get the sock anyway. Who wants a 400 meters long sock anyway? You know, it's absolutely useless. Also in collaboration with Professor Simon Niedenthal, you see here, this is the kitchen at my house here in Malmo. During the pandemic, Simon, who is the professor in interaction through smell, is a very unique professorship that exists only here in Malmo, in the whole of Scandinavia. We were working in making games to retrain the sense of smell. This is scent bottles. The kits of scents, they come in kits with 54 bottles. And Arduino would read an RFID card in the bottom of each one of the scents, and we could just make games in Unity where you were asked to combine different scents. You had to go around smelling scents and putting them in the reader and see if you were combining the right order and so on. But on more serious stuff, for example, SAS land vehicles were geofenced using an Arduino board that was turning them off if you were driving them out of the premises. Or a doctor student from Malmo University, he was trying out a fuel consumption system for rockets controlled with an Arduino Mega on the European aerospace zero gravity flight. So this guy worked for a year to make a 10-second test. And he trusted Arduino to make this test, which means, you know, this tool that was made to help design students to make prototypes could actually be used for very serious stuff. So we've seen all sorts of projects done with Arduino. But this takes us to the present. And in the present, 8-bit boards, which is what Arduino was built on, don't really make a lot of sense any longer. People are not using them a lot. And I will come to this idea of 8-bit boards later on. This is a current Arduino Uno board. There's 2 versions, one without Wi-Fi and one with Wi-Fi and 96 LEDs, because you want to have LEDs for everything. And the interesting thing is that we could have the same price we had for the old Arduino Uno with nothing to have everything, as you can see here. So currently, there is a demand from the community in adding more and more stuff to boards. The current present is people want to have more features, more sensors, more things, okay? Which is, in a sense, in contraposition to this idea of making things more sustainable. Because the more things you add, the more specific, the more components you put, the less sustainable things tend to be in the long run. But to talk a little bit about how things are made, Arduino's documentation, for example, is completely open source and is built on state-of-the-art technology. And I would like to invite anybody here to hack Arduino's website, and please let us know. I'm saying this because the whole Arduino's website is basically plain HTML. There is no interactive components in it, so good luck. You have to basically have to hack Cloudflare. If you do that, you will hack us. But I spent 2 years of my life doing the architecture design of this. So currently, 100% of the Arduino knowledge is contained in a single GitHub repository. You can go to the Arduino-docs GitHub repository, and you will find everything you see on the website. So we have done scripts that renders the plain text from there into a website. It also renders all of the PDFs, because for some reason in the world of electronics, people want to consume PDFs instead of plain text. So we first generate PDFs and then generate a website that contains PDFs. And everybody's happy. And everything is open, by the way, it's Creative Commons, so you can use it in whatever way you want. And this is the Arduino IDE, which is under GNU license, and is probably one of the most downloaded tools that exist on the internet. It's downloaded once every 2.5 seconds. So as I said, this sentence is downloaded 5 times. I rehearsed this, by the way. I hope this gives me points in the evaluation of the talk. And as there are many developers in the room, one of the most common problems we find is when people want to make commercial products out of Arduino tools, because they say, oh, but this is under GNU license, or, well, the Arduino core, which is what you use to compile your programs, is under LGPL. So if you have an urge to close your source, that's really up to you, then you can do it. Nobody's going to ask you to share the source with them. At the same time, the challenge you're going to find is there is many libraries. There's thousands of libraries in the Arduino ecosystem. So we created this website here that allows you to find which kind of license you want to work with in your libraries. So you say, oh, I would like to have LGPL libraries. You click on LGPL, and then you get a list of libraries that will allow you to work under that kind of paradigm. So we have all sorts of boards, and we have different form factors. I think the concept of form factor might sound stupid to you, but it's actually very, very important. The Arduino form factor, which looks a little bit ridiculous, 20 years ahead of time, it was created because I was teaching a lot, and I had to draw boards on the whiteboard, and drawing a rectangle didn't really help students that had problems connecting cables to it, because nobody knows in a rectangle what's left and what's right. By giving it an uneven shape, it was always very easy to understand, oh, what's left, what's right, what's up and down. But people really like to have different form factors. They want to have boards that they can easily connect and hide inside a lot of small stuff. So the Arduino Nano is probably the most extended form factor that currently exists. It's a board that is the size of my thumb, more or less. You have a smaller thumb, it's not your thumb, okay, it's my thumb. I have a really big thumb, just to. But the community develops its own form factors, and one of the most successful form factors comes from a doctor from MIT, Leah Buckley, who was interested in understanding the relationship between fabrics and electronics, and she's the creator of the Arduino LilyPad, which is a board used for wearable computing. And she's been very open and published all of her processes. I love this slide very much, that she made with collaboration with Make Magazine, where she's showing how she went from putting a microcontroller on top of a piece of felt with like conductive fabrics, and all her process towards making a piece of hardware. It's interesting because he was doing a lot of workshops teaching people basic aspects of electronics, where they will learn in a conversation with the material and with the workshop leader. Like, oh, this is an LED, works this way, and you have to saw it this way, and people will figure out how to make it function and so on. But in the end, what people will make is always embroideries. This is probably the most famous embroidery ever made by Becky Stern. You can still find it on the internet. It's a nice piece of work. And then there's, of course, collaborations. I have to ask before I show the next thing, is there anybody from Sony in the room? Good. Okay, so Sony made a smartwatch in 2012. And as you know, Sony, even though they're getting less and less people involved in work, but they used to have a lot of people working in Lund. And at some point, one day having a cup of coffee, somebody said, oh, this smartwatch runs on a microcontroller. Couldn't we just have it running on Arduino? And we said, well, for an undisclosed amount of money and some beers, we can do it. And they said, what about pizza and beers? And we said, okay, yes. So in a matter of a week or something, we had we had a meeting in Lund where they show us some files on their screen because we're not really allowed to get files. And based on what we could read and remember, we managed to hack the smartwatch and get it to work this way. The only thing we couldn't get to work was the Bluetooth stack. So you could do a lot of stuff with the watch, you could reprogram it, you could use a touch screen and so on. We had some people that were programming a Star Wars game on it, like kind of like an asteroids game. It was very interesting. It was a lot of fun. But at the end of the day, what you would do with like the Arduino workflow is like you had any kind of hardware that, as long as you could figure out how the basic reprogramming mode worked, you could hack it into the IDE and use the core of the Arduino system, which is compatible with any kind of tool chain, to write code for that specific piece of hardware. So we created this kind of abstract layer that you can put on top of your software stack to then compile for anything. You know, we had boards with Intel, we had boards with almost anybody. But I guess one of the important things to talk about is embedded artificial intelligence, what we like to call as TinyML. And when we went into the world of TinyML, we started because we had a board that was supposed to be able of doing computing blockchain to send sensor information to the internet, making sure that people's data would not be compromised. So we made this board called the Arduino Portenta H7 that, of course, we use to play Doom, because that's what you do when you have a board. This is actually true. This is Arduino Portenta H7, which has a dual-core processor, Cortex M7 with Cortex M4. In the Cortex M4, you can put the whole of Doom, and through the USB-C connector, you can use the screen and play Doom on a proper HDMI screen. I think it's pretty cool. And you still have the Cortex M7 to do other things. But with the same processor, we created a board called NICLAVision, which is 2.5 times 2.5 centimeters, that has a camera, an accelerometer, and a microphone, and that you can use to do what people are doing in TinyML currently. Currently, in the last 2 years, TinyML has been about computer vision. Really, if you look around, all of the boards that are into TinyML are basically doing computer vision. It's like cameras will save the world. So this is just one of the cameras that exist. There's others. And what can you do? Because you have two processors, you have one processor running an inference engine, separating cans from bottles, while the other processor is running MicroPython, and you can tweak the algorithm as you are doing things. The interesting thing with this board is that it's very lightweight in terms of power consumption. Just fun facts. The engineer doing most of the software for this thing lives in Helsingborg. And he never comes to the office, because we accept remote workers. Apply to Arduino. This is my... But then, so we do Linux quite a bit. And Portenta X8 is this board here. You see that runs Yocto Linux as a way to allow you to have fleet control and do wireless reprogramming of boards all over the place. And you would say, David, it has no pins. And I will say, well, you have to look closer. It does have 160 pins on the back. So you can plug a lot of LEDs to it if you want. The interesting thing of this board is that it has hardware encryption. You can do fleet control over the air, and it runs Docker containers. So you create your thing in Docker, in your computer, whatever, and you just deploy Docker containers onto it. Again, it's a bit expensive, so you only use it when you have like a relevant industrial thing. But then last month, we just launched this, which is Arduino Uno Q, which is an Arduino board that can be running the Qs for Qualcomm, obviously. It can be working by itself, connected to a computer and a mouse, and you can run it also as a tethered device. And what did we do with it? We played Doom. Okay, you are an experienced audience. I don't need to explain you that Doom is a de facto way to try FPS, right? How many frames per second can you render in a machine? So this video was sent to me this morning, and I really want to get a GIF of this video to put it in my slides, because I have a talk today. So this is fresh, actually fresh from this morning. So, but David, what is that you actually do at Arduino? It's a question you should be asking yourself. I'm obviously not a marketing expert. It's not my thing. I do research. This is actually part of my research. It's my PhD, where I cover the history of Arduino. So if you If you are really bored, I recommend reading this book. If you are insomniac, it will help you sleep. 1 page a day, the doctor will say. I, for example, studied the relationship between social groups and technology. This is a study I co-authored with Cesar Garcia, where we studied how when you remove the political component of hacker groups, like, you know, the original hack labs in Spain and Italy in the 70s, 80s, they were extreme left-wing. And as you remove the political component, you increase the amount of people participating in them. At the same time, that's what we call commoditization, okay? At the same time, the more you remove the political component, the more viable is the experience, is the commodification. So nowadays, in the past, being a hacker, it was dangerous and bad. So it was kind of like, now you don't want your daughter to like run away with a guy in a motorbike with tattoos, right? But nowadays, being a hacker is real cool and you can be a billionaire. So you really want your daughter to run away with a guy on a motorbike and tattoos. So by removing the political component, suddenly the concept of hacker transformed, and then parents want the kids to be hackers, which is the complete opposite that happened 20 years ago. So that's what we studied in this particular study. And then, of course, there is Minecraft. So this is a study that we're going to build now, where we're going to look at using this new type of board that runs Linux and embedded code as well. What we can do is that we can reprogram the board from Minecraft running on the board. This sounds a bit like Inception, okay? So you get the Arduino Uno Q, which is a Linux computer, and you run Minecraft on it. You run a Minecraft server on it. And then in this environment, you find books. The books contain Arduino code that you can then modify. And as you modify it, the code is being uploaded to the microcontroller, and you can control the physical world. So what we want to analyze now in our research is how much kids learn to program, especially kids who are used to playing virtual worlds, the moment they see that the virtual world can affect the physical world. So we're still working on crafting the research question, but as you see, this is part of our future work. And again, this is from last week. I want to give you a book recommendation. I haven't written anything on this book, but I've read it left and right. So if you're interested in the relationship between society and computers, Your Computer is on Fire is a really good book to get started reading about anything computers. Has, for example, an analysis on how much energy the cloud consumes, has an analysis on how IBM perverted. Is there anybody from IBM in the room? It's a study on how IBM perverted the union systems in Germany after World War II. I mean, everybody knows what IBM did before that, but we don't need to talk about it. I have friends at IBM, so let's forget about that. Anyway, so it's a really good book that will introduce you to the different challenges that computers bring to everyday life. And one of them is sustainability. And so this is my focus, and this is actually the core of my talk, really. And I have about 25 minutes to talk about it. And I want to talk to you about making electronics sustainable, possible approaches, and which is the approach we're taking at Arduino in collaboration with other partners in Europe. So I want to talk about the Desire for EU project. And if anybody's want to take a picture, could you please take a picture of this now with me in the picture and send the picture to me? This is for the social media of the project. This is very good for the European grant, okay? Okay, so Desire for EU, and as you know, European projects are famous for the really bad acronyms, means designing and recycling sustainable electronic boards for a European circular economy. Basically, we're looking at how to get every single part that exists in the process of making a board, the board itself, and the process of recycling the board, put it in a life cycle analysis and trying to understand how much is the impact of this. And then trying to figure out parts in the process of making boards that could be hijacked or hacked to be changed and have a less impact in the environment. Okay. So let's look at the future. In the year 2525, David Cuartielles III has finished making a project, and he wants to reuse the processor. So he puts his board into a microorganisms bath that will eat the different parts of the board, and he can reuse the processor into his new project. Okay, this will be a beautiful future and a beautiful grandson as well. So back to the present, thing is that we can already take away components and reuse them, while it was considered a bit of a greenwashing action by Apple, Robot Daisy was able of dismantling and repurposing the components in iPhones. So this is a present, okay? It's also possible to use to reuse biodegradable parts by using bioreactors and decomposing them in order to use them again. For example, if you take biomass, which is the leftovers from cutting a forest, for example, and you put them into a bioreactor, you will get biofuel on the one side and bioplastics on the other side, for example, as possible outcomes. So if we could make a bioreactor where you could put electronic boards inside, then we could probably reuse things. And this is not so stupid, because if you think about it, electronic board substrate is called, which is called FR4. Well, there is many other ones, FR1, FR2, FR3, but FR4 is the most used one, okay? It's made of a mix of glass fiber and epoxy. When you compress glass fiber and epoxy together, it becomes a very durable material, almost too durable. If you depose it in nature, it will take hundreds of years for it to degrade. And that's really the challenge. The challenge is not really taking out the metals, which is hard. The challenge is that the substrate itself is stronger than concrete. So we need to, first of all, we should think about what to do with these electronics instead of sending them to a waste land in Nigeria, which is what we're currently doing. And we should figure out how to change that. So the proposal we're having is that what if we change the substrate of boards with a biomaterial? In particular, in order to do that, we need to rethink about how to manufacture printed circuit boards. Do you guys know how a factory works to make printed circuit boards? I'm going to show you. So there's hundreds of processes to make printed circuit boards. I'm only going to show you a couple of them, and I will highlight why I think they're important. For example, when the substrate comes, we glue a layer of copper on the top and a layer of copper on the bottom. If a board has more layers, you keep on adding substrate copper, making a huge sandwich with many layers, okay? So the first thing you do is to put it in a CNC machine, and it drills holes on it, and are the holes that you will see in circuits. Then these holes, they will be plated with a material. There's different materials you can use for plating. You can use silver to plate, you can use tin to plate, you can use gold to plate. Depending on the kind of circuit you want to have, you will use different materials. And then everything really boils down to a very long production line like the one you see here. This is, by the way, Alba PCB, a factory in Venice, Italy, where we make all of the Arduino boards, which are 2 layers. The yellow things you see on the back, they are cranes. And the cranes, they take big sheets of copper boards where we have been drawing the circuits we want to etch, and we dip the boards in acid. And as we dip them in acid multiple times, they etch away the copper that we don't want to stay on the board. Okay, first we make holes, then we take away what we don't like, okay? And then the thing you see in the front is a washing line. So the boards go through the different layers of washing with different kinds of products. We use tens of thousands of liters of water to take away the remains of the acid and the remains of the paint that protects the layers we don't want to take away by the acid. So it's a very water-consuming process. This is an example of a product that was allowed to photograph. It's a part of a sensor. And you see the sensor is repeated multiple times. And because when you etch things, this movement is like it reminds me of my grandmother, like washing things when I was a child. You take the thing and you etch it, you put it in, you dip it, and you take it out, and dip it, and take it out, you know. This movement makes the acid etch things away, but it's not uniform in the way it etches. It etches differently in the borders than in the center of materials. So that's why you have to figure out different lattice structures to fill in the copper, so the etching on the border will be uniform in comparison to the center. In this case, because the design is a very simple linear sensor, this lattice is very simple. But imagine you have circuits with like a lot of chips and a lot of lines and so on. It's a lot more complex. So these things is based on experience. And here we have Oliver, super happy. And he's in front of a machine. That's an oven that will cook circuits at 100 degrees for 1 hour. This is done after you apply paint on them. The colors you see is a paint that you put on top of the copper to protect it from the environment, because copper has a tendency to oxidate real quick. So you paint it. And they have to harden the paint for an hour at 100 degrees. And I say in the 100 degrees for a reason. Just keep the 100 degrees on your mind, okay? And then, of course, there is some mechanical processes, like, for example, the robots that are measuring every single connection, electrical connections, to make sure that electricity will flow between the points that it should. So there is 70. I only show you like 5 processes. There is 70 processes in a PCB factory, 70. So there is so many points of intervention to make things greener, okay? And then there is also how you build boards. You add components to boards. So boards come to a factory. This is Omaric, the factory that assembles all of the Arduino 2-layer boards in Italy, in the Piedmont. And Sarah here is explaining, some researchers from our project, how every single Arduino board gets etched a QR code so we can trace back all the components on that board. Because in order to make sure that you're making the best for the end user, you have to be able of tracing when boards don't work. And there's many ways. One of them is QR codes. And then things go through a pick and place machine where you put the components. And here's the secret sauce of Arduino. You see here's an army of testing machines. Arduino for real is a software company because manufacturing is a commodity. There's hardware factories all over the world, not so many in Europe, but there is many, okay? And you could manufacture your things anywhere. You just have to make sure they have the quality you want from these people, right? The different factories. So what we have is machines that we can put in place, and they take every single board that we manufacture. It's not a sample, it's every single board. And we're talking 5,000 to 6,000 a day. And they're putting these machines to measure whether they work or they don't work. And from here, they go to packaging. So we have a team at Arduino that's dedicated to only create these machines and ship them all over. In this way, we could open a factory in India last year to manufacture for the Indian market by just shipping the machines there. So according to ST Microelectronics, if you want to make ecologic designs, there's 5 steps where you can intervene. At Arduino, we're focusing on product development and manufacturing because it's the things we do. So how do we design things and how do we make them? And so if we want to change something, one single part of the whole process, we have to look at how the different steps will change within this. So our goal is to change the substrate, which is this epoxy with glass fiber, for PLA flax. Flax is a fabric, and PLA is a plastic used for 3D printing. So I have to ask you this question. How many of you have been 3D printing at all? Okay. Do you know at which temperature PLA melts? Are we talking? Okay, sorry, you scared me. I was like, I'm going to ask you, are you talking Fahrenheit? Yeah, it's true. So it depends on the quality of the PLA. So it's from 180 to 220, depends a bit. So PLA melts at relatively low temperatures. The oven that solders the components to a board works at 350 degrees. So if you made the PCB in PLA and it went through the oven that is going to secure the components on the board, that's at 350. What you will get at the end is flan, as we say in Spanish. It's nothing, basically. It's components in a ball. So we have to change the temperature for soldering, basically, right? So it's possible. We've been experimenting with these companies, Meshining and Meshlink from Hungary. They're responsible for making the substrate for us. What you see here is a microscopic cut of a PCB made of PLA flax. If you take the FR4 boards, the ones that you have in your electronics all over the place, and you cut them like this, what you see is a very fine grain. You will not see this kind of like almost interferences, right? These artifacts. I like to compare it like if you have ever played with wood, if you cut MDF is made of powder and glue. It's very fine. When you cut it, you don't see a difference between the top and the side. But if you cut conglomerate, you see these kind of layers like this, okay? So the organic, the biodegradable PCB is basically the equivalent to conglomerate. If you were in Spain, I would say it's like a Spanish omelette because it's made of a lot of piece of potato like this, glued by egg, okay? But we're not in Spain, so I cannot compare with anything in Sweden. Anyway, so there's many challenges because of this. For example, when you drill this material, if you drill FR4, it's like drilling MDF, so you get out the powder. But if you drill this material, there is a lot of like tiny hairs that come out that will clog the drill. So every time you make a couple of holes, you have to bring the drill back to clean up. So every single process of making a board is affected by the change of the substrate. If you drill too fast, this material will melt because it melts at lower temperatures, right? So you have to be very careful how you drill as well. So new materials require new processes. This is really a big part of this. But we are not reinventing the wheel here. I want to say there is a lot of science currently. This is just systematic research made on looking at making green PCBs. This is the amount of papers academic years made by year. We can see how it grows linearly year after year. This is only made until early 2024, so that's why these numbers like stop here. But you see there is an increasing amount of research being made in this. For example, some research from some of our colleagues in the project, they've been looking at how to make green PCBs and how it affects high-frequency circuits. You see here an FPGA from Xilinx, and how they're making a green circuit and then trying out how the signals are affected because the dielectric is different. I'm sorry if I'm too technical. I hope this will not affect my scores, but we are supposed to be very clever humans here. And as I said, one of the challenges is soldering. The typical solder tin used melts at really high temperatures, but there is other tins that melt at lower temperatures. There's other substances, and they're equally successful at conducting electricity. So it's possible to solder at 60 degrees. It's possible to solder at 120 degrees. You have to change the chemistry of soldering. This is actually, again, a paper from one of our colleagues that has been published. So with all of this, here we are today. So I want to introduce you to Arduino Nano on green PCB. And green is not the color, green is the material. And also Arduino Uno on green PCB. So these two boards have been manufactured using the substrate I was talking about. And you see there is some differences. For example, you will notice, for example, on this board that every hole is double, okay? You will see that every connection opens up in a 45 degrees angle to embrace the next component, and so on. So these are interesting differences that we are detecting that will ensure that manufacturing will reach 100% yield, which means that all boards will work at birth, which is not very common. So if you're interested in everything I said, this is the important slide. I'm not going to read it, but these are the design guidelines to making green PCBs, okay? You have to change a little bit the way you design. We have reached a point in electronics design where everything is possible. But if you really want to make something sustainable and you want to introduce changes in the process, you have to figure out how those changes have to be made and what will work. And then there is bioleaching. Bioleaching is a science fiction part of the project, and I don't have a slide about this because this is work made by the University of Leuven, and I want to tell you about it. So we as humans, we have been contaminating the world massively for quite a while. And one of the ways to contaminate the world is by washing mineral. When you go to a mine, you use water, typically groundwater, to wash the mineral coming out from the mine before you send it to the next step of processing. That water you use typically has microorganisms. Well, it turns out the copper mines have grown microorganisms which are resistant to copper. And not only that, they can eat copper. So bioleaching consists in using microorganisms to eat the copper out of the boards. So in our dream bioreactor, the one that we're trying to build in this project, what we're going to be doing is to take these microorganisms to eat the copper out of the boards, and then what remains, put it in a different type of bioreactor that will dissolve the PLA and give it back to the earth. So you see, so it's a very interesting process. We want to reuse 90-something% of the copper from the boards with a 96% purity, which is enough to make boards out of boards. Okay, this is the goal in the long, long run. And there's still research to be done. And I want to show you a bit of the composting work. For example, I want to be very clear, PLA is not biodegradable, okay? I'm talking all the time about biodegradable, and we see PLA as just one step towards the final goal. PLA can be destroyed, can be made into microplastics, but it's not necessarily biodegrading in the way that you might understand it. Like, you understand biodegrading means, oh, I put my banana peel and it becomes nutrients to my plant automatically. But PLA will not become a nutrient to your plant. Not now, it will take some years. But we can decompose boards in 48 hours. Our goal is to decompose board in 24 hours by the end of this project. And what you see here is PLA boards being degraded, and this is a microscopic picture of the PLA flags being broken after 48 hours. And what you see here is a happy worm. It's the first worm eating Arduino boards. We still don't have a name for it, so please send me names. So with this, we want to formulate 2 principles, and with this, I'm ending in perfect time with my talk. First one is called manufacturing, and we talk about it as lowering the temperature of production. So as I told you, this life cycle analysis, which is a very complex process that covers a lot of steps, what happens if we manage to lower the temperature in this process? What happens if a factory that typically works at 350 degrees for soldering works at 120 degrees for soldering? We're using less energy. We need to use less power from that power plant to run the factory. It's definitely not linear. So if you have less the consumption, you don't really, you have less amount of power, you don't have like less the consumption. It's not linear like that. But we're trying to figure out which is the right equation. And the other concept is what we like to call just enough technology. So if you reach the quality and reliability for your project to do the job, why do you want more? So if everything I need to work with a computer is a text editor and a spreadsheet, why do I need an NVIDIA video card? So that's a bit of the thinking here. So if we have reached, for example, an understanding of which are the tools that most people need in the world, then we just need to figure out which is the minimum common denominator to make sure we have a working computer and a working sensor board that works for everybody the same. And typically have compatible pinouts. I think compatible pinouts is probably the most important part. If you think about it, before I say the next thing that's going to sound completely alien, how many of you studied digital electronics? Nobody. How many of you ever, if I say 74LS00, what do you say? NAND. It's a NAND gate. Okay. It's not the right crowd. It's fine. But what happened in the beginning of digital electronics is that there were a series of chips that had compatible pinouts, and they were manufactured by different companies, and they competed to see who was making it the cheapest possible. But nowadays what we have is dedicated chips that are different between all manufacturers. So if I need to change the processor for my board from company A to company B, all of a sudden I need to redo my whole design. But wouldn't it be great if I said, I need to throw in a Linux processor in here, and I knew the 128 pins of my chip were compatible, and I had to choose between the companies offering me the best features versus price. That would make that all of my PCBs will be the same. And then the manufacture and recycling will be much easier. And if I wanted to have a faster computer, I would just take out my processor and put a better processor, and that's it. So that's the concept of just enough technology. And this is still in the making as a concept, but we will see where it goes. So what we're doing with this project is to design a very simple microcontroller board, 4 layers like this, and we're going to give 2,000 boards away for free. So if you're interested in trying them out, reach out to us in the late 2026, when we will have changed the whole factory to be able of manufacturing green boards, lowering the temperature or the different production steps, and put them out for people to try out. We're going to run a massive beta testing with people, and then we will recall some of these boards back and leach them with our cultures of bacteria, and then see if we can recover the copper out of them. This is the goal of this research project. This is the way the board looks like right now. It has a STM Cortex M0 chip here that's capable of doing some machine learning for limited size, but still enough. And LoRa radio. So if you are looking at making green PCBs using green PCBs for your remote control garden, this is probably your best friend. Okay, guys, now that you know this is possible, why don't you do it yourself? Thank you very much.